Wonderful. Yeah, so yeah, this is the first time I heard all that stuff, and fortunately it was quite synergistic to my talk, so there's no objections there.
Are you going to disagree?
No, I'm not going to disagree. I'm going to give or propose a metaphor that structures his research into some wider framework so that we can have some sort of map of our understanding of AGI. So I call this this model, this metaphor, Quaternion Process Theory of Cognition. So it's basically paying homage to Kahneman's dual process of cognition. Has everyone read Thinking Fast and Slow? Right. So it's based on that concept of what Kahneman describes in human behavior, that there's this fast thinking that is unconscious, and there's this slow thinking that's deliberate. Okay, who am I? Right. I'm a software architect by trade. Right. I've been doing software development for a couple decades, and basically in a lot of different AI-related areas, parallel computation, distributed agent performance, subsumption architectures, constraint programming, decentralized ledgers. That's not AI. Sorry. Search engines, machine learning, and today LLM powered solutions. And my passion is to work on ideas that have a long shelf life. Right. So I've written a couple of books. In 2017, I wrote a book based on Kahneman's ideas of Thinking Fast and Slow. So I called it artificial intuition, and I just recognized that what we see as deep learning during that time was something you could describe as Kahneman's fast thinking or artificial intuition. And that eventually a lot of the pioneers of this field started using that to describe deep learning and explain why it was missing the slow thinking part. And then during the pandemic, I wrote artificial empathy, and yeah, during pandemics, you want to write a book. So this is my book. So I had to change the font so that it would actually fit. So that's what I was going. And I'm working on another book now. It's almost complete, Artificial Fluency, and this is really to address, to get a better understanding of the advances in transformer models like GPT-4. And I have more pragmatic books. I have a Deep Learning Playbook in 2017. Pattern Language for Generative AI. That is a book about creating a pattern language for prompting design, in GPT-4. And then I'm working on another book that, because of all the developments in RAG and tooling and that sort of thing, I needed to expand the ideas beyond just prompting. Okay, why do we need good metaphors for AGI? So for centuries, we relied on metaphors that were like machine. So we would model things, our mind, our thoughts like a steam engine, our memories like hard drives, our reasoning like logical algorithms. So, but we're seeing the limitations of that model, right? So GPT-4, everyone sees GPT-4. Okay, I assume so, right? Because some people don't pay the $20. Has challenged our assumptions about what it means to be intelligent. Right? But we must be cautious about mistaking fluency, which is GPT-4, with actual understanding. Right? So to truly understand the potential limitations of the new AI tools, we need a more powerful metaphor that can capture the fluid, dynamic, and creative nature of human thought and communication. So I propose a more comprehensive metaphor. Language is a living process. So yeah, if you think about it, right, humans are limited in understanding through metaphors. And what is the biggest hyper-object that we can think of, that we're familiar with, right, that we're immersed in? And that is language. Right? So I think in terms of what you call a bridge object to understanding, then I propose that we should focus on language as a living process as our metaphor. Okay. Oh, by the way, this was written by Club. Okay, so we want to anticipate AGI's development. So between 2012 and 2017, we had artificial intuition, which was deep learning. And then 2017, 2020, guys wrote attention is all you need. We had transformers. By somewhere in 2020, GPT-3 came out. That's artificial fluency. Toward the end of 2023, GPT-4 came about, right? And then we have another transition. I don't know what it is. Maybe it's artificial empathy. We'll find out. But there is this accelerating curve, right, of short cycle. You have shorter time lengths, right, and exponential growth. Right. So let's talk about the first part, okay, artificial intuition. Right, there are two axes here that I have. One axis is in terms of processing. So you have parallel processing and meta-reflective processing. So one is in parallel, the other one is sequential. And the other dimension, right, you have representation. One is iconic, analogical, things that resemble each other, and the other one's indexical, causal, things that lead to some other concept. So like a pointer, if I point to something, I point to the laptop, that's an index. It's not really what I'm pointing, not really my hand, it's the laptop that I'm referring to. Okay, so we're all going to frame that, the next images in terms of this axis. So after artificial intuition was discovered, we discovered artificial fluency, which I call fast fluent. And that's the transformer model. And the overlap of this is when you had the two technologies come together and you get these artistic capabilities in diffusion models. So you have to understand that diffusion models came around 4 or 5 years ago, but we were never able to control it until we actually merged it with a large language model. So in these diagrams where you see the overlaps is where the two capabilities are combined. Oh, another point. Yeah, there's something I refer to time travel development. And the very curious thing about large language models like GPT-4 is they're able to reason about causality up to a certain level, right? And the thought probably a few years prior that you needed embodiment to be able to understand causality, but apparently they didn't need to do that. What they did was train to understand programming. But the curious thing about that is that programming is like a futuristic idea in terms of biology. Biology doesn't write programs. So what we're actually doing is we're taking something in the future and training these new kind of agents. So I call that time travel development. The next, so present day, this is present day AI, this is today. Right, so we add another, the green circle, right? So this hybrid artificial intuition plus artificial logic, algorithms, right? So in the overlap, what you see here is creative, causal, holistic, coherent, and this is the slow, fluent, systematic kind of reasoning. So you have the you have the thinking fast and slow here. This is thinking fast and this is thinking slow, right? And usually when we think about thinking slow, we're actually thinking from the point of view of something verbal, right? Something in terms of language, right? So if we're doing math, it's in terms of language and there's intermediate steps. So all that you have today is captured in this diagram, right? So you're thinking slow, right? You have chain of thought kind of things, the RAG things or search, right? In the overlap, right? You have coherence between the fast fluent and the slow fluent, right? And then you have, in the overlap of all three, you have the causal capabilities. Okay, this shouldn't be here. We'll see that later. Okay. Now let's add another diagram. Another circle, the red one, right? Now all of a sudden, as you add this circle, right, you have all of a sudden these new capabilities: persuasive, abstractive, creative, paradoxical, strategic, and this thing I call slow empathy. The question is, what could slow empathy be? Right? We can understand slow fluent as being something that we perform step by step. We perform through a scratch pad or a notebook, right? But what is slow empathy? So slow empathy must be something that must be reflective. At the same time, it's analogical, iconic. Right? Okay. So when I built artificial empathy, I had a hunch that it might be very important, so I wrote it, right? And I proposed a roadmap that begins from the point of view, it leverages Udaya Pearl's ladders of causation, right? So it has this interventional and counterfactual, right? And then after that, you have level 5, that's conversational, and then essentially at level 6, that is a linguistic culture. So one good analogy of something that's slow empathy is our civilization, where we've built languages that coordinate parallel agents to get stuff done. Another analogy of a possible thing that might be slow empathy is that you're doing your research, you're picking up ideas left and right, and one day you're in the shower and you go, aha, right? You have an aha moment. Now, where does that come from, right? It's not necessarily a deliberate kind of intelligence, but something that takes parallel perspectives, multiple perspectives, and just merges it, collapses it, right, into a single idea. But you don't know when that happens. It just happens while you're taking a shower. So this is tomorrow's AI empathy, and I've annotated this with possible technologies that might support each one in the overlap. Right, so in the abstractive, one of the weaknesses of deep learning systems is that they don't know how to abstract. They don't know how to create abstractions. And the problem is when they approximate another system is some massive piecewise approximation. And the problem with that kind of representation is that you don't have reach. You don't see where it can be modified to do something else. Right? So we need basically some sort of system that will create newer abstractions. And I'm banking on this notion of using pattern languages, where pattern languages, who's heard about pattern languages? Oh, so pattern languages is something that was that came out about 2 decades ago, and it was used in architecture, and then eventually moved into software development. But the whole idea of pattern languages is to basically take tacit knowledge in a field and make it explicit. So what you're doing is your tacit knowledge your tacit knowledge creates a new vocabulary that you can use within your community to basically improve the designs of that community. So they did it in architecture, and they did it in all sorts of fields like software, object-oriented design, and user interface design. So that's what pattern languages are. Right? Let's see. Yeah. So there, and then so these are my proposals, possibly of what may implement these different missing pieces. So that gives you an idea of where we're going. And the most interesting part, which I'll cover later, is these paradoxical models. Okay. So let me show you how I derive this. Right. So one easy way you might think that you can derive this is there's thinking fast and slow, and then there is probably this idea of left brain and right brain, right, where you have a kind of logical sequential thinking and parallel empathic thinking. So that's four. So that gives you the four diagrams, right? That's one way to think about it. There's another way to think about how you might derive this, and this comes from ideas from 1899. Is that correct? 1899, right?
Wrong.
By Charles Sanders Peirce. Peirce was actually a logician, and he laid out basically how you would organize all of knowledge. And underneath this ontology, right, he has logic, right? But his logic is a superset of what we understand as deductive logic today. So his superset includes three things: speculative grammar, critic, and some weird name, right? And the thing about, the problem with reading Peirce is he invents words. So, because he doesn't have the correct word for it. So, I mean, the concept wasn't invented, so he creates a new one. So that's why it's very difficult to understand his writing. Plus, he changes the words over time. So, and he died never publishing his work. So it's a complete mess. Okay, well, let's look at the first. Right. Oh, and another thing about Peirce is he always goes by three things. That's his idea of triadic thinking. I'm not going to explain that because that's a little dense. Okay. In the first part, right, this is called architectonic. That's what he called it. So the first kind, right, are these is what's normally understood as semiotics or the study of signs, right? He called it speculative grammar, right? And this is basically different signs have different properties. So if you look at a sign, right, in Peirce's, normally when we think about Peirce or semiotics, we only think about icon, index, and symbol. But actually, Peirce actually has 10 different categories. This is a subset of that 10. So this is only the three, right? And even looking at this three, right, you recognize that the combinations mean something in terms of how they're used by the different agents, right? So, like, one is like money, for example. Money is a coordination mechanism, right? And it has these properties of being a proposition symbol type, right? Why is it symbol? Let me explain. So in semiotics, there are three kinds of symbols, or not, three kinds of signs, I'm sorry. There is the iconic sign, which is something that resembles something. There's the indexical sign, I mentioned this earlier, something that points to something. And there is a symbol. What's a symbol? Something that is just by convention. So the word dog, the word dog, D-O-G, we understand it to refer to the four-legged animal because it's by convention. It's a particular norm, right? So money is a symbol type, right? Why? Because money is just a convention. It's just imagined. We just imagine that it has value. Okay, second item in that architectonic tectonic structure, inference or critique. Right? So Perez identified three kinds of inferences: induction, deduction, and abduction. And that forms actually a cycle of creativity and innovation. So you start with a model, you develop an intuition out of it, right? And as you develop that intuition, you have a new vocabulary where you can apply deduction to expand into new conclusions, and then you have abduction to basically create new theories, and then you have a new model again, and it's a cycle that repeats itself. Okay. Third, right, the third level is rhetoric, discourse, and methodeutics. Okay. So Perez identified this category, but he never wrote anything about it, or if he did, it barely. There wasn't much about it, and there's also, he didn't identify the three elements in that category. So remember, Perez always does things in three, right? So when you have a category, there must be three things in there, right? So I've identified those three things, and identified what they were. These are cognitive processes. Okay, and the first kind of process is like a dynamic process that has an attractor or a limit cycle. So these are as an example, hurricanes, iterative systems, deep learning. So they through iteration, they reach an orbit that is stable, right? But over time, right, it dissipates like a hurricane. Or in an iterative system, because of chaos, depending on the parameters, right, it could it could diverge or it could converge, right? So that you get the mandible set for that. The next kind of process requires two processes. And this is called co-dual process, right? The first person who came up with the idea is, it comes from biosemiotics. It's called co-duality by Jesper Hoffmeyer, right? But the notion is that you have two kinds of processes. One is discrete, right, as in fast fluent, and one is continuous. And that combination gives it greater permanence. So you see that in life, in cells and DNA, right? So if you think about biology, right, the DNA by itself cannot create the cell, right? The cell must exist to interpret the DNA so that you have a replication of that cell, right? It's the incorrect notion to say, once I get a DNA, if I get the DNA of a mammoth, right, I can replicate the entire mammoth. No, what's missing information is the actual cell, which is gone forever for the mammoth, for the woolly mammoth. And the last kind of process, I call it the tensegrity process, right? An example, life, right? Life and AGI, right? Life requires three things: DNA, proteins, and lipids, right? And then I can explain later, some other time, why this is a tensegrity process. It shows three, but it's actually four. Okay, what is tensegrity, right? Who's familiar with that word? Yeah. So these are these structures that look like they're floating. So I bought this recently, right? So it's like a platform. These are just strings, and there's a gap there, right? That's just a magnet, right? That pulls it, right? But it appears that these things are bootstrapped, like they're floating, and then you can extend it forever, right, into longer structures. So this is a good metaphor for things that are balancing, like in life, for example. Okay. So this is cognitive tensegrity. Okay. So you start with the fast empathy system, right? And then you get this this dual, right, process, right? And then you combine the two co-duals into the tensegrity structure, right? And one is in tensegrity. I'm sorry, I forgot to explain tensegrity. Tensegrity requires two forces. One is a compression force, and one's a tension force, or right? the reason why this looks counterintuitive is because most of our buildings only use one kind of force, compression. Right? We don't, other than probably bridges, that sort of thing. Right? So this looks unintuitive to us because we don't see it often enough. Right? But you have these two forces that are in balance to give you a structure that is both rigid and flexible, adaptable. And you want that structure in AGI. You want the precision, the rigidity and accuracy in AGI. At the same time, you want the adaptability. And these tensivity processes can be expanded into all sorts of collaborative processes that we see in the human collaborative field. Okay. And
3 minutes and no questions, if possible.
Huh?
3 minutes and no questions, if possible.
Okay.
Do you need more time?
I'm almost done. Okay, I just need a slide. Okay, so I don't know if everyone's seen there was this paper by Deep Learning that tried to explain whether AGI is here or not, right? So they proposed something that was more like a spectrum, and then we're somewhere in there, right? And I'm proposing not just a spectrum, but maybe possibly a path that tells you exactly what's right, rather than, in this case, it's just saying better, 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 or more better. And I think that should be it.
Any questions here? We have 5 minutes for questions. We'll wait 5 minutes if nobody else. In silence. Yes.
If those were mountains of that we're climbing, and some you know, like that it had a how do you say a relief in English? Landscape, I guess. So what would the landscape look like in terms of things that are further away from us in this
In terms
on
of
the
distance,
diagram.
right. So there is a there's a layering here, right? So the more overlaps, the farther away it is, right? 2 overlaps, it's closer, right? That's all I can say.
So it's all symmetrical.
What do you mean it's symmetrical?
So the highest one is the holistic one, and there is no.
Oh yeah, because that's all 4 overlaps.
Right.
I don't know what the holistic one is.
Right.
So leave it as is. Right. Oh yeah.
I'm curious, are you familiar with ideas from semantics of programming languages, particularly the ideas of denotational semantics versus operational semantics?
Notational versus operational. Is that declarative versus imperative?
Denotational semantics maps program fragments to some kind of mathematical object.
Yeah.
Right. Whereas operational semantics tells you what you need to do.
Right. So it's declarative versus imperative.
Yeah, exactly. So that strikes me as similar to your integrity metaphor. That there are these sort of two sides of the of the problem. Whenever we are faced with modeling some kind of problem, there is the process part. How you instantiate that, for instance, in nature in some way, and there is the ideal that the process represents that can never actually be realized in nature, and yet in some sense it is the true identity of the thing that we're modeling in the process. For me, this is one of the things that current AI systems just don't really tackle in any way. It's a very difficult problem to how to have these things that understand exactly in terms of the process that approximates the thing and the abstraction, the ideal that is generated by the process.
Oh, okay. So let me try to frame this. So a declarative language really just tells you what's the shape of the system that you want to build, and it sort of like fills in the gaps, right? So like SQL, for example, right? SQL.
So that's a little bit different. A good example would be, for instance, a circle. You cannot realize a circle in nature, right? Like at some point of resolution, you're going to see that it's not a circle; it's only approximate.
Okay.
So you might have a process that will lay out the atoms, but at some point your atoms are going to be basically the pixels of reality,
Okay.
or whatever particle you can find. But a circle exists as a thing somewhere, right, in this abstract space,
As a concept.
Yeah, as a concept. So the denotation of a process might be a circle, but operationally it's, I don't know, like an array of
but
atoms.
right. Yeah, but yeah, so mathematics always has some idealization of the real world, right? It has infinite precision, which is not possible, right?
Yes.
It assumes infinite precision, right? So, but that is really the distinction between the map and the territory. So when we're talking about abstract things, right, we're talking about just maps, but the maps are never the territory, right? That's why there are limits to simulation. Simulating something, we won't get certain emergent behavior because the simulation is not the same as the actual thing you're simulating, right? Or you can even take that to a higher level. You have the irreducibility that you have in like the halting problem, right? You can't predict the behavior of another Turing machine unless you're the Turing machine itself, right? So there's this gap between the abstract, right, which is the map, and the territory. The problem is, right, for people who are computer science and mathematics, the map is the territory. So you don't see that distinction. But people who are in science, who do physics and chemistry, they see the distinction all the time.
Answer your question, Christoph? We have 2 more minutes for questions.
No one else. I'd love to hear a bit more about. I found the idea of time travel development super exciting. Do you want to say a few more words on that?
Oh yeah.
Maybe.
Yeah, it's a very curious thing, right? So when GPT-3 came along, right, 2020, was it 2020? I looked at it and said, you know, it doesn't do causality very well, right? It just throws out gibberish words, right? And my thinking back then was, it needs embodiment, right? It needs to be participating in this world to be able to understand causality. So a lot of like reinforcement learning is based on that idea, right? That you participate in this world and you eventually figure out the causal relationship, right? But large language models didn't require. I can't find it. Okay, didn't require that. How they circumvented that for GPT-4 was they did instruction training and programming codex training, right? And there's a speculation here that no large language model is capable of causal reasoning without codex training, right? So they kind of circumvented biology in the sense that biology doesn't know how to program, right? It doesn't have that data, right? So they took something from the future and basically brought it into the past to bootstrap it.
How sure are you about the biological bits not being able to program?
Oh, the
Because
program
we-
in the
because of-
sense. Oh yeah, program
because of-
in the sense of human programming. In other words, you're creating abstractions, right, to drive an imperative. Right. So this is if you're talking about biology programming, then maybe it's kind of more like a diffuse kind of creating something, but not in the sense of actually creating abstractions. So when we go to programming, right, we actually build simple models, right, that we can understand to create what we're the kind of
I
information.
see what you're saying exactly. I think now, but I feel like there is a spectrum. So DNA is also using abstractions to create proteins, and of course there is an interpretation of that code and so on. If you're aware of that, and we talked about reservoirs before the event started, right? This is another example of that. But it feels like there's something. Maybe there's a spectrum, and that's what you're suggesting. It's very interesting. I feel like it's a very soft separation, but there's still programming in biology.
Right. But the thing here is the time travel development is that you did the actual system, because the original idea of deep learning is the reason it's different from Go5, which was programmed, is you want the system to learn how it got to where it understands things, But in this case, right, it didn't need embodiment, right? It got that knowledge from somewhere in the sky, right? Humans, right? And we gave it programming languages.
Yeah, let's continue that.
Alright.
You think like my previous supervisor does, which I partly agree with. Let's continue later.
You end up getting everybody to Kyoto
That's right.
or DC.
All right.